AP Physics Workbook, Unit 5 Momentum, Activity F, Conservation of Momentum, Elastic Collisions. Please remember to pause or rewind the video as necessary. Read the scenario along with me, please. A toy car is pushed with speed v towards a toy truck initially at rest. The car bounces off the truck so that the final velocity is v over 2 in the opposite direction. Consider the system to be the car and the truck. There's our system right there. Now, what we know is that in all collisions, momentum is conserved, meaning if this is the system, that means the truck will apply a force on the car will apply an equal and opposite force on the truck, and there are no external forces on the system, which means momentum is conserved. The momentum before the collision equals the momentum after the collision. Well, we could go ahead and solve this problem to find out the relative velocities, I guess you would say, after the collision, and we can use that to relate to the bar graph that we're going to produce for momentum in part A. So before collision, you only have one object moving. Now I'm going to consider the van to be, or the big moving van to be mass 1 and the car to be mass 2. So M1V1 initial plus M2V2 initial equals M1V1 final plus M2V2 final. Now, the van is at rest, so it has no momentum beforehand. The other vehicle, the little car, is moving in the negative direction. So M2V2 initial would be negative, would be M, the mass here, times negative velocity. And we're told afterwards that the car's final velocity, basically it hits this and it bounces backwards, right? So after the collision, the final velocity of the car, rather. So we have M1, which M1 is the van, so that would be 3M times V1 final. We don't know what that is yet. Plus the momentum of the car, which is just mv, but we're told that it bounces back with a speed v over 2. So I'm going to put that in there like that. Now, let's just go ahead and solve this equation for v1 final. Well, I'm going to take mv over 2 and subtract both sides. And I get negative mv minus mv over 2 is negative 3 mv over 2 equals 3 mv, 3 m v1 final. The 3's will cancel and the masses will cancel. So in other words, v1 final is equal to negative v over 2. So what happens after collision, the car, the little car, if this barrier represents the collision, the little car is going to bounce back at a velocity v over 2, and it's going to impart a force on the moving van, which causes the moving van to go this way at speed v over 2. Now, of course, the velocity of that would make it negative, but the magnitude of that, of course, would be the same as this right here. So, and we can represent that in a picture. And what I'll do to represent the picture, I'm going to make yellow the moving van, and I'm going to make, yellow the car and blue the moving van, just so you can understand the color coding of my bar graphs. So what I'm going to do is I'm going to go ahead and say that the car's momentum is, I'll go ahead and scale it something like this, about every, so M, 2M, 3M, every 2 boxes is M, every 4 boxes is V. Okay, so I'm going to use the same scale for all the graphs. Go. Go, and one more. Okay, there we go. And so I'm going to say, if this is the scale I'm using, that means that the little car would have negative velocity of, remember, the car has mass and going in the negative v direction. So mass times velocity, that is your mv. But notice your MV is highlighted as 8 boxes in my bar graph. So I'm going to put a little -8 in there just to kind of quantify the bar graph, so to speak. Okay, the moving van has no bar graph, so I'm going to put a line all the way across it because it has no momentum beforehand. The truck's momentum is 0. Now afterwards, the little car of mass m bounces to the right, rebounds, backwards, but in half the speed. So half the speed would only be to this point right here, which would be v over 2. And the truck, which has 3 times the mass, would rebound at half the speed, but in the negative direction, to the left. So if you count the boxes, they do add up. So I have -8 to start with right here. Here I've got, which means before the collision, I should have a relative value of -8. Means after the collision, I don't know why I wrote M final, should be P final. After the collision, I should have a relative value of -8 too. Well, I've got 4 here, and I've got -12 here. 4 plus a -12 is -8. So you can see how the momentum is conserved in this bar graph. Part B, how does the situation change if we consider the system only to be the car? Well, if we only sketch the car, here's what I'm going to do. I'm going to copy down the graph for the initial momentum of the car, exactly as is. Just like that. Okay. Now, what we have is we have the car the final momentum of the car is only, oops, wrong color. Let me fix that. Okay, so if we're talking V, 2V, -V, -2V, here's M, 2M, and 3M. The initial momentum of the car, and let me adjust this, make it a little bigger. There we are, okay. So that we have 8 boxes shaded in there. We're only going to have 4 boxes shaded in here. Now, how do we go from having a momentum of -8 to a momentum of +4 box units? Well, you had to gain momentum of 12, right, in the positive direction. That would be, of course, the impulse. So I'll do that in a different color, like black. So we have an impulse of 12 units that are added to the -8 momentum to give the +4 momentum. And again, -8 and 4 are just relative terms, but it's there to help quantify the values. Now, part C. In the laboratory, a ball is dropped onto a force-sensing platform several times, each time hitting a different surface, foam, feathers, clay, etc. The momentum of the ball changes by the same amount in each trial. In each trial, the average scale reading is F. The time of the collision T are measured. What quantities would be needed to graph to exhibit a straight line relationship? Justify your answers in a few sentences. Well, the concept, if you're trying to drop an object onto several different surfaces and you're plotting force and you're collecting force data and time data, the concept is impulse. It's change in momentum. So this is an impulse lab. Impulse is a change in momentum. And so using net force times time equals a change in momentum, we can separate the net force and time, and we get net force is equal to 1/2 times delta P. Now, if I write that one more time, net force equals, I'm going to write delta P up front, times 1/T. You can see that matches up with y equals mx plus b. And you can see we would be plotting net force versus the inverse of time. And the slope of the graph would be your impulse or your change in momentum. AP Physics 1 Workbook, Unit 5, Momentum, Activity G, Ballistic Pendulum. Please remember to pause or rewind the video as necessary. Read the scenario along with me, please. A small dart of mass m is launched at angle phi above the horizontal with speed v0. At the moment it reaches the highest point in its path and moving horizontally, it collides and sticks with a wooden block of mass m that is suspended at the end of a string of negligible mass. The center of the block is a distance L below the pivot of the string. The block and dart then swing up until they make an angle theta with the vertical as shown at the right. Air resistance is negligible. Well, clearly you can see the first part of this problem is a projectile motion problem. Okay, now let's go ahead and begin part A. Sketch the horizontal and vertical velocity time graphs from the time the dart is launched to the time it hits the block. And then part 2, determine the speed of the block just before it strikes. Your answers should include V0, phi, theta, L, and physical constants. In other words, your answer can only include these, nothing more. Okay, we'll get to that part. Well, first of all, we're referring to just this part right here, okay? Now, one of the things we should remember about a projectile motion, when it's launched, so we have a initial velocity, we'll have V0 x, which is going to be V0 times the cosine of the angle, and you have V0 y, which is V0 times the sine of the angle. And I'm kind of in just, I guess, a habit writing angle theta. We were told that this is angle phi, so I should write it like that. Now, what happens, of course, if you remember, as the projectile goes up, okay, the horizontal velocity remains constant because there are no net forces horizontally. So the horizontal velocity stays constant the entire way, all the way until hitting the block right there. The vertical velocity, on the other hand, well, it starts off with a certain value. That's going to be V0 y, and it's going to get smaller and smaller until Vy is 0 at the top. So let's consider this time right here. I'm going to consider this time on both graphs, which I'll go, let's say, 1, 2, 3, 4, 5, 6, 7, 8. I'll just go 8 blocks over. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm going to go 8 blocks over, and that's going to be the time when it hits the block. So this is, I'm going to call time t the time that it takes to go from here to here and hit the block. Okay, now the horizontal velocity should be constant the entire time, and the value of that should be V0 cosine phi. Whatever your initial value is, that is the same value all the way along, because remember, horizontal velocity stays constant. The vertical velocity, on the other hand, is going to start at some value and it's going to decrease to 0 all the way at the top. Okay, so the speed of the dart when it hits is only due to the horizontal velocity, which means the speed at the top is going to be v naught cosine phi. Same as the horizontal initial velocity. Now, we identified part B, we identified the system by including a circle of both the dart and the box. So there's our system, the dart and the box. And let's go ahead and make a momentum graph for this. So what I'll do is I'll go ahead and, again, I'm doing a relative sketch here. I'm not going to go in terms of certain values of boxes here. This is just a very relative sketch. But here, basically, what's going to happen is we're going to start with a certain amount of momentum with the dart. The dart's momentum is going to be m, and the velocity is going to be v naught cosine phi. The block has no momentum to begin with because it's at rest. And then afterwards, the block and the dart stick together and start swinging, but since they stick together, they're going to have a much lower speed. Greater mass, but lower speed. And so you would expect something like this, where this includes the mass of the dart, right, plus the mass of the block. That's why the bar graph is wider. And you can see the velocity is shorter because this is the velocity of the dart plus block together. Part C. In a second experiment, a dart with a greater mass is launched at the same angle and speed. The dart collides and sticks with the wood. Wood angle theta and the dart of the block swing to increase, decrease, or stay the same. In a clear, coherent paragraph response that may include figures and or equations, justify your choice. Well, so here's if you go back at the picture, the first part of this problem is, and I'm going to go ahead and erase some of this here so I can use the picture again. The first part of this problem is conservation of momentum. Okay, in other words, mass 1 v1 initial plus mass 2 v2 initial equals m1 plus m2 times v final. This is an inelastic collision right here. Okay. Now, this part of it is conservation of energy, in which case the kinetic energy that you start with, 1/2, and I'm going to use big M to represent the total mass added together. So 1/2 mv squared, the kinetic energy of both the dart and the block, begin to swing upwards and they become the potential energy at the highest point. Well, mass is independent when it comes to the energy portion of this problem, okay? That's not the issue. So if you were to say that the angle theta would stay the same because of this reasoning, I mean, you might be right, but you'd be forgetting the fact that the problem starts as a momentum problem. So if you launch the dart with more mass, so let's say I do this, I make this mass 2m. Well, then that means I have more mass before collision, I have more momentum before collision. That means I have more momentum after collision. More momentum after collision means I have a greater speed of the block and dart after collision. Greater speed after collision means I have more kinetic energy after collision. More kinetic energy after collision means I have a greater potential energy after collision, which means I have a greater height. If I have a greater height, the pendulum swings to a greater angle. Let's summarize all of that in a paragraph. If the mass of the dart increases, then the initial momentum also increases since P equals mv. Momentum would still be conserved since there is still no external forces on the dart block system. If the initial momentum before the collision is now greater, due to a larger mass, then the final momentum of the collision will be greater. This means the post-collision speed will be greater. If the post-collision speed is greater, then the post-kinetic energy of the dart pendulum upswing will also be greater. If the kinetic energy is greater, then the potential energy that it converts to will also be greater. This, of course, leads to a bigger angle. So there will be an increase in angle theta. AP Physics Workbook, Unit 5, Momentum, Activity H, Experimental Design, Impulse. Please remember to pause or rewind the video as necessary. Read the scenario along with me, please. Carlos and Dominique have been challenged to design an experiment to determine the impulse given to a cart as it collides with a barrier using two different mathematical or graphical ways. Dominique sketches the following diagram of her laboratory setup and writes the procedure below. So if you can see what she's doing, she has a ring stand and a force sensor set up over here. A cart, a dynamics cart is just a cart with low friction bearings so that it can move at a constant speed across the table. There's a cardboard target here that is directed in the, on the same side as a motion detector. So what happens is the cart is basically being pushed this way away from the motion detector. It's going to collide. The dynamics cart will collide with the ring stand, with the force sensor, to essentially establish the impulse, the change in momentum. So you can see the materials would include a computer to register the information from the motion detector, the force sensor, which is right here, the motion sensor, which is right here, the cart, which is right here, the cardboard target on the cart, and the and a mass balance, which is not in the picture. The mass balance, of course, is to measure the mass. Part A, experimental design. Edit Dominique's procedure for length and clarity. Cross out any unnecessary statements. Change the order of the statements. Correct any statements for errors. And write new sentences if necessary. Okay, so first of all, let's begin with the idea that you do not need to say gather all materials. Not necessary. Well, nor do you have to say record the mass in the actually, no, that would be a good place to start right here. So what I'll do is I'll highlight the ones that we're going to keep, and I'll cross out the ones that we're going to get rid of. So record the mass of the cart would be a good place to start. We do not need to say plug in anything. We do not need to check that devices are working or talk about how we set it up. We do not need to say that we're attaching the motion to sensor. We do not need to say that we have to align the motion sensor in the car. We do not need to say that we have to create. There's a lot of unnecessary statements, as you can see. We do not need to say that we set the motion sensor to record in cart mode. None of that's necessary. Okay, but now we get to step 10, begin recording force and motion data. Okay. Give the cart a push, away. So you're telling the person what to do right there with the cart. That's good. Part 12, after the cart collides with the stop recording the force. Yep. So 12 works. Number 13, determine the impulse. Yes, but this one, how? How do you determine the impulse? So this 13 is a little incomplete. We'll fix 13 in our steps. 14, repeat the steps. There we go. Repeat the steps. We're all looking for that. And 15, clean up lab state. No, we do not need to say that. So we can really have a procedure with just steps 2, 10, 11, 12, 13, and 14 kind of looking like this. Part 2, record the mass of the cart. Step 10, begin recording force and motion data with the computer. Step 11, give the cart a push toward the force sensor and away from the motion detector. Step 12, after the cart collides with the force sensor and has bounced back, stop recording the force and motion data. 13 is what we have to expand upon. Instead of just saying determine the impulse, well, how do we determine the impulse? So we can determine the impulse by analyzing the information on the force time graph that's created by the force sensor. The area under the force time graph is the impulse. The impulse can also be found by looking at a velocity time graph. Remember that impulse is a change in momentum. So you can find the velocity before and after on the velocity time graph, before and after the collision, and that velocity before and after times the mass would help you find the momentum before and after, and thus the change in momentum. Okay, repeat steps, step 14, repeat steps 10 through 13 with different initial pushes, again, to reduce error. Part B, sketch a graph of velocity as a function of time and what the force as a function of time should look like. Well, the cart is going away from the motion detector, and then all of a sudden it hits the force sensor and bounces back. So this is the speed, this is the velocity before collision. This whole acceleration here, the whole change in velocity here, that is the collision. And then this would be after the collision. Okay. Now the force sensor that would be created, of course, it would be no force, no force, no force, and then all of a sudden there'd be a spike like this, and that triangular region right there would represent the change in acceleration or the net force that you experience, and the area under that, of course, would be the impulse. Part C, explain how these representations can be used to determine the impulse given to the cart during the collision. How could you use them to determine the impulse given to the cart from each graph? Well, remember, impulse is a change in momentum, or mass times a change in velocity. Therefore, looking at the velocity time graph and recording the cart's initial and final velocities here and here, the impulse can be created, it can be calculated. Also, impulse is the area under a force time graph. So if you were to find the area under that, you'd be able to find the impulse as well. AP Physics 1 Workbook, Unit 5, Momentum. Activity I, Momentum Representations. Please remember to pause or rewind the video as necessary. Read the scenario along with me, please. A ball is thrown straight up into the air with initial speed v0. After a few seconds, it returns to height from which it was thrown. Air resistance is negligible. Sketch the following graphs as a function of time as the ball is in the air. Well, something going straight up and down, the position time graph. This is, keep in mind, this is vertical position or height, because the ball's going in a vertical direction, would look just like that. Now, the velocity graph, you'd be starting with an initial velocity. It would decrease to 0 over time and would keep going after it goes from the highest point, would go in the negative velocity. So the ball goes up, stops, goes in the negative direction. The acceleration is constant the entire way, and that would be due to gravity. The potential energy of the ball-Earth system. Well, potential energy, the gravitational potential energy is mgh. So wait a minute, potential energy is dependent on h. Therefore, the potential energy graph would look exactly the same as this graph here. Now, the scale would be different because it's h times the weight mg, but the shape of the graph would be exactly the same. The momentum of the ball. Well, momentum is equal to mass times velocity. So the momentum would start off positive, go to 0 at the highest point, and end up negative on the way down. So the momentum time graph would be the same as the velocity time graph because, again, momentum relates to velocity times the mass. And then net force is equal to ma. So you would expect the net force graph to be constant, just like the acceleration graph is constant. Now, total mechanical energy of the ball-Earth system is going to be constant all the way across, but the kinetic energy graph, well, the kinetic energy graph will look the opposite of a potential energy graph because total energy has been conserved. You start off with kinetic energy, you end up with minimum kinetic energy at the highest point. The ball has to stop momentarily when it changes direction, and then it's going to come back around and gain kinetic energy on the way back down. Part B. The following sentences discuss the relationship between these graphs and the physical ideas they represent. Fill in the blanks. Number 1, the slope of a position time graph is equal to the average velocity. Number 2, the slope of velocity time graph is equal to the average acceleration. Number 3, the area of the acceleration time curve is equal to the change in velocity. Number 4, the area under the velocity time curve is equal to the change in position. Number 5, the graph of momentum time is the same shape as velocity time graph because momentum is equal to mass times velocity. Number 6, the net force graph versus time has the same shape as the acceleration versus time graph because net force is equal to mass times acceleration. The slope of momentum time graph is equal to the net force. Now, let's see how that one makes sense. Let's back that one up for a second. So, momentum versus time. Momentum versus time. Let's go back to the graphs. Well, the slope of velocity versus time is the constant acceleration that you experience here. So that should make sense. The slope of this graph would give you the net force. Number 8, the area under the curve of the net external force versus time graph is equal to the change in momentum, or the impulse. Number 9, the potential energy versus time graph has the same shape as the vertical position graph because the potential energy is equal to mgh. Now, the kinetic energy versus time graph is related to the velocity time graph. It's not the same, but it's related to it because kinetic energy is involved with velocity and is equal to 1/2 mp squared. Now, the total mechanical energy graph is constant, because it represents the sum of kinetic and potential energy versus time. Also, there are no external forces on the system, so there is no work done. Therefore, the total mechanical energy is constant. AP Physics 1 Workbook, Unit 5 Momentum, Activity J, Explosions. Please remember to pause or rewind the video as necessary. Read the scenario along with me, please. Angela and Carlos have identical masses, big M, and stand on identical light carts with bearings of negligible friction. Carlos holds a heavy ball of mass, little m. At time equals 0, Carlos throws the ball so that it has a horizontal velocity v while a projectile. At time equals big T, Angela catches the ball at the same height from which it was thrown. Okay, so we have two things going on here. Well, conservation of momentum is all over this problem. And remember, conservation of momentum means that the momentum has been conserved. Well, before Carlos throws the ball, so you have big M V equals little mv. So Carlos's momentum is going to be equal and opposite to the ball's momentum. Now, if you think about how that works, momentum initial equals momentum final. But Carlos and the ball have no momentum to start with. That means they should have no momentum to end with either. But because he throws the ball this way, his momentum is that way. The momenta of the ball is the same as the backward momentum of Carlos. Now, since the ball has little mass, it will have a bigger velocity. Since Carlos has a much bigger mass, he will have a slower velocity backwards. Now the ball itself is going to travel and is going to be caught by Angela. This, ladies and gentlemen, would be an inelastic collision where two masses are coming together and colliding. What's going to happen is you're going to have M big V, which is the ball's momentum, same momentum that it had when it left Carlos, is going to be hitting Angela. Now, she has no momentum before collision because she's at rest. But after collision, you have her and the ball's mass, right, times their speed together. So they're going to go off with some smaller speed together. So you've got M plus big M times much less speed after they collide. Part A. Which student moves faster speed for time after time t? Okay, explain your reasoning. Okay, so after time t, that's after Angela catches the ball, who's going to be moving faster? Will Carlos be moving faster backwards because of his throw, or will Angela be moving faster because of the ball colliding with her? Carlos has a faster speed. Because the original momentums of the system, the two students and the ball, is 0, the final momentum and the momentum at the time in between must also be 0. When Carlos throws the ball to the right, the ball's momentum is directed to the right, while Carlos's momentum is equal and opposite to the left. The momentum given to the ball, mv, has to be shared between ball and Angela. That means Angela's speed will now be smaller than Carlos. Let's quantify this in part B with equations. Derive the final velocity of Angela after collision and the final velocity of Carlos after collision, or after his throw, after his explosion. Again, for time, little t is greater than big T, just simply means the time after Angela catches the ball. In terms of big M, which is the mass of Carlos and Angela, little m, the mass of the ball, and v, the velocity of the ball. So it's telling us what to do over on the right-hand side. We're just going to work it out symbolically through equations. So to begin with, the system and the Carlos. Okay, so we're going to start off with this part right here. The system is Carlos and the ball. Angela's not a part of the picture yet. There are no external forces, so the momentum is conserved. So let's start off with the change in momentum is 0. Initially, Carlos, which is big M, and the ball, little m, are at rest, so their momentum is 0. So I'm going to expand this equation right here to look like mv plus mv equals mv plus mv. Now, what does this look like? Okay, now take some time to make sure you get the variables right. This would be mass 1 times the velocity of Carlos initially. Okay, remember, and then so mass 1 would be big M. Okay, and then the little m times the velocity of the ball initially. Okay, now after collision, you've got the mass of Carlos times the velocity of Carlos after collision. And so this would be velocity final for Carlos plus, write this, velocity initial for Carlos, velocity initial for the ball. Okay, there we go. Sorry, just rewriting the equations. And then mass times velocity final of the ball. There we go. So we're starting with the idea that initially the ball and Carlos, oops, there should be an equal sign right there, have no momentum beforehand. And so how does that change the equation? Well, 0 equals 0. Well, how do you get two momenta to equal 0? They have to be equal and opposite to each other. So now what we're going to do is we're going to solve the equation for the final velocity of Carlos, right here. And so the final velocity of Carlos is equal to negative m times v final of the ball, the final momentum of the ball, divided by big M, which is the mass of Carlos. Okay, now we're on to Angela. Okay, so far we dealt with the explosion, all right? Now we're going to deal with the inelastic collision that happens with the ball and Angela. So again, for the second part of the problem, the system consists of the ball and Angela. There are no net forces, therefore the momentum is conserved. So we're going to start off with delta P equals 0. No change in momentum through the collision. Now, initially Angela's at rest and the ball's momentum mv means that the ball's final momentum must also equal mv. After the collision, the ball and Angela have a new velocity, v final Angela. Okay, now let's see what this would look like. Well, the final momentum of the ball after Carlos releases it is the initial momentum before reaching Angela. So I'm going to write the exact same thing. mv final of the ball right here is mv initial of the ball as it approaches Angela, plus mass times velocity initial of Angela, which is 0 because she's at rest, is equal to the mass of the ball plus the mass of Angela times v final for Angela. Now it's final for Angela and the ball because she's holding the ball, but I'll just call it v final Angela. Now finally solve for v final Angela by dividing by the sum of both masses, and it is the initial momentum of the ball, the final moment, well, it's the initial momentum of the ball before catching Angela, but it's the final momentum of the ball that left Carlos. Remember, it's the same. It's the momentum of the ball divided by the sum of the masses. So if you look, how does this help explain how Carlos moves faster? Carlos's speed is this right here. Notice the numerator, let's just talk about the speed, so don't worry about the negative, okay? The numerator is the momentum of the ball. The denominator for Carlos is just his mass. While when Angela catches the ball, it is her mass and the ball. Since the denominator is greater, her speed has to be less. Part E. Let E1 be the mechanical energy of the Angela Carlos ball system before time equals 0. So before time equals, remember, at time equals 0 is when the ball is thrown. Okay, so before time equals 0 means before the ball is thrown. And we're going to let E2 be the mechanical energy between when Carlos throws the ball and when it reaches Angela. And then E3 is going to be the mechanical energy after Angela catches the ball. Well, the lowest would be E1, okay? So I'll get to my ranking in a second. E1, there's no mechanical energy. Carlos hasn't thrown the ball yet. Carlos is at rest, ball's at rest, there's no mechanical energy. So E1 is going to be the lowest, okay? For E2, the system has mechanical energy generated by what Carlos does work to throw the ball, okay? And then E3, some of the mechanical energy is lost in the inelastic collision with Angela. So there's going to be less mechanical energy in E3 than in E2. So you should get a ranking of E2 has the most when Carlos throws the ball, between the time Carlos throws the ball and while it's in the air, and E3 when Angela catches the ball, and then E1 obviously would be the lowest because there's no mechanical energy at all before he even throws the ball.